So we are trying to predict the pH of weak acids. We just got off of the exam, and before we took the exam, we talked about predicting the pH of strong acid solutions. Well, pretty much all the acids involved in these pictures, whether you're brewing commercial products, that's going on in the dump or in the lakes, it's all weak acids. So this, being able to predict and try to control the pH of weak acid solutions is probably a little more applicable than strong acids. And that really begs the question, Sabina, how did we know we had a weak acid in the first place? How do you know the difference? How do you recognize the two? You have to know the strong acids, because then everything else is a weak acid. So definitely know those strong acids, otherwise you're not going to be able to tell which is which. Okay. So for any weak acid, let's pick on Crystal Munoz. For any weak acid, HA, we're just going to mess with some terminology and try to get used to it. We're going to write its acid ionization reaction. They also call it the dissociation reaction. And if our weak acid is HA, how do you think you would write this? This weak acid dissociating. HA, good, goes to H plus, and we're just missing one little thing, A minus, the conjugate base, right? Because they have to be conjugates. Good. And one thing that I'm just going to be honest with you, we're getting really lazy on, and I'm leading this, is we should be writing AQ on everything. But I think this is probably the one and only time that I am, because it has to be there. These are all our aqueous solutions. Everything's dissolved in water. Okay. Vivian, how would we write the equilibrium constant? Now we call it the acid ionization constant, or the Ka. How would we write the Ka expression for that reaction? It'd be what over what? H. Now it has to be H plus in what, though? In brackets. And in brackets over HA. So since there's a subscript on this equilibrium constant, you have to write the reaction a certain way. In fact, you have to write it this way. The acid always is the reactant going to H plus in its conjugate base. You have to write it that way. Otherwise, these Kas that are all in this nice table, like that in 16.1, you can't use them. They're all going to be incorrect. So you have to write the reaction the right way. And that pretty much works for any equilibrium constant that has a subscript. Okay. See if we can play around with this a little bit. Danny, what would you guess? A blank acid ionization constant, a blank Ka, means that it is a stronger acid. Would that be larger or smaller? She's larger. She's right. Do you know why, though? Because what are all equilibrium constants? They're all what over what? Products over reactants. H plus is a product. Yeah, so if you want a stronger acid, you need more H plus, so yeah, that means a larger Ka. So that means it is a stronger acid because of a blank degree of dissociation. Anybody? Because of a higher degree of dissociation. Because how we should be writing, this is really misleading, this arrow. We should really get rid of it. It has to have the double arrow. And it's majorly pointing in which direction? Towards the reactant or the product? The reactant, because it's a weak acid. So it should look like this. Now, the small of arrows you can write go into products, because that's really what this is looking like. But again, we'll never be doing that, but that's the idea. Okay. And pretty much in every single case for weak acids. Table 16.1 lists the acid ionization constants for some weak acids. Okay. Crystal Zamora, which acid listed would you say is the strongest? I would too, but it's not It's ordered in alphabetical, not strength.
Oh, so you have to look at the KAs?
Good. So you got to look at the KAs.
What's the greatest?
Yeah, which one would that be? I think I see it. So looking for the biggest number. Which one do you see as the biggest?
Oh, hydrogen sulfide?
Hydrogen sulfide. That HS minus? This one?
No.
Right. So what's the biggest number? Is it going to be 10 to the minus 13 or 10 to the minus 2? 10 to the minus 2.
So whatever has the least.
Yeah, so you want the biggest number.
Sulfuric acid?
Okay, now here sulfuric acid is 1.3 times 10 to the negative 2.
Oh, phosphorus.
Is there anything bigger than 1.3 times 10 to the negative 2?
Phosphorus. No, wait. Oxalic acid.
How about this one? Okay, which number's bigger? I just want us to get used to looking at these numbers. Which one looks bigger? Yeah, 5.6 times 10 to the negative 2 is really 0.056, really. This is 0.013. Yeah, so oxalic acid would be the answer. H2C2O4. Okay, how about the other end of the spectrum here, Alyssa? What about the weakest? Which is HS negative. Oh, where did it go? That's this one. Is there anything smaller than that?
Which one?
It's a number smaller than 1.2 times 10 to the negative 13. Does everybody agree? Yeah. Right, because the other one, 10 to the negative 13, is just a little bit bigger. That's 4.8. So HS minus. Okay. A little more practice here, Gabby. We want to write the dissociation reaction, so something going to something, for the weakest acid in the table. How would you write the Ka reaction? I like to call it the Ka reaction, but how would you write the dissociation reaction for the weakest acid in that table? Now we said the weakest acid was hydrogen sulfide. So how would you write the Ka reaction for that? Oh, this is the expression. It's not the Ka expression, the reaction. So it wouldn't be concentration, it'd just be HS, the what charge? Right here. HS negative goes to H plus and excellent. Right? You see how she did that? So it has. So what we are writing. So this is the how you write the Ka reaction of any acid. You always put the acid on the reactant side, its conjugate base on the product side with an H plus. And remember, to write that conjugate base, you have to subtract an H plus. So that S minus went to S minus 2. Perfect. Make sense? Okay. Now they also want the Ka expression. So I would call this the Ka reaction. But now they want the Ka expression. So Sabina, how would you do that? The Ka expression. That's just equals. Uh-huh. Mm-hmm. Yeah. Right? And they're all going to be there because everything's aqueous. So we're not going to be leaving anything out. Okay. Good. So what we are going to do is we're going to jump right into these problems here. Just quickly. First, we're given acid ionization constants, all these Ka expressions for all these different acids, and we just want to know how to write the reaction that corresponds to this equilibrium constant. That's pretty much all we've talked about so far, right? And it has to be the acid going to H plus and the conjugate base. So now we're jumping changing gears a little bit, we want to calculate equilibrium concentrations. Before I even go on, just this statement alone, calculate equilibrium concentrations, pretty much, Erica, means what? We're going to have to do what? If we're after equilibrium concentrations, we have to do ice. You can't avoid it. If we're after equilibrium of any reaction, you got to do ice. So you know we're going to be doing ice. Okay? And we're going to be doing ice on weak acid solutions when we're given a Ka. So it really doesn't matter what you're given, you're going to have to do ice. Okay. Formic acid is used to make ethyl formate, artificial aroma sweetener. What is the pH of a 0.1 molar solution of formic acid? Okay. Tegan, what is the equation for pH again? I know I give you all this stuff, but what's the equation for pH? Negative log of H plus. All right. Now, is that the equilibrium concentration of H plus? Everybody? If you want to measure the pH of a solution, you take the hydrogen ion concentration and the negative log of it. Right? That would be the equilibrium concentration of H plus. Otherwise, the pH would be changing on you. Right? So this has to be the equilibrium concentration. Now, where do we get these equilibrium concentrations? In which row? In ice? The E row. So we're going to have, it's going to look something like this. You're going to have ice, and then wherever H plus shows up in the E row, wherever it shows up, that's what you plug in. Okay, so we need a reaction if we're going to do ice. Sabina, what do you think that reaction probably will be? What reaction would we be doing ice on? Yeah, the Ka reaction. And she said that's going to be the HCHO2, keep going, goes to, what are the products? What are the products on a Ka reaction? Right? They're always H plus and the conjugate, what do we call it? The conjugate base. So H plus and the conjugate base. Here's H plus. What's the conjugate base? CHO2 with a minus. Perfect. Okay. Now, just like before, we don't do any calculations inside that ice table. You make a complete ice table and finish it, right? So, Crystal Munoz, how would you do the I row? Is there anything even to put in the I row? Okay, the 0.1 molar. Where does it go? Perfect. 0.1 molar. We don't put in units, do we? We just kind of put in 0.1. What do we put in for H plus and formate? Dashes. Good. I should move my box over a little bit. My H plus is right here. Okay. The change row. Vivian, what did we do for that again? Negative X. Yeah, for products, they're always positive, right? For products, they're always positive X. The equilibrium row, our answers are at the equilibrium row, Danny. You'd have what then? 0.1 minus X, X, and X. Okay. Oh, Crystal Zamora. We're after the negative log of H, which is going to be the negative log of X, because X is H plus. Now what?
I don't know. I'm guessing we have to use that Ka.
The Ka expression, right? Because sometimes they give you one of these equilibrium concentrations. Then you don't have to write the equilibrium constant expression. But they didn't, right? They didn't say, oh, at equilibrium, the formate concentration is something. So we have to write that Ka expression. And that Ka expression right? H plus formate all over this. Now, a lot of folks like to skip this, but I don't think it's a good idea because it's so easy to screw up. Now we substitute it for these concentrations. Those are all equilibrium concentrations. You got to substitute in your equilibrium rho. So what would be on top, Alyssa? X and X. And on bottom you'd have 0.1 minus X. Oh, what should I put in for Ka? Yeah, 1.7 to 10 negative 4. Okay. Now, do you remember how now there's going to be something that you're really going to like. It doesn't look like you're going to like this. But I'm telling you, you're going to like this. Imagine if you could, now first let's see if you remember how to do this the hard way, right? We had to bring the 0.1 minus X up there with the 1.7 to the negative 4. Then we multiplied everything through. We ended up using the what expression? Quadratic formula, quadratic expression, right? So it got really ugly and really ugly fast. Just imagine this. If I could erase this, what the math looks like. What would you do now? Move this up here with this, then what? Because then you have this number equals x squared, square root both sides. You'd have your x, no quadratic formula. Okay, what would be the argument for removing this? For saying 1.7 times 10 to the negative 4 is approximately x squared over 0.1. How can you say that? We need an argument to do this. We want x to be really, really what? Then we can do this. Small. You want x to be really, really small. And then you can do this. Then it doesn't matter whether it's 0.1 plus x, 0.1 minus 2x, 0.1 plus 3x. You don't care. X is really small. You always drop this plus or minus x thing. And all you have is your number. And it wouldn't matter whether it's on the top or the bottom because x is really small. Now, there's a way that you can look at this number, at this Ka, and you can say that x is going to be really small. If this Ka is really what, then x is really small. If the Ka is really small, x has to be really small, right? Because Ka's, or any K, is what over what? Products over reactants. X's are your products. So if your K is really small, dang, yes, we can drop these x's. So the question really comes down to what makes a small K, right? Because at some point, you can't drop this x anymore, and you're going to get the wrong answers. Because the Ka, right, the x won't be small enough. So the rule pretty much is, and we're right at the border right now, 10 to the minus 4 or smaller. You could say when K is 10 to the minus 4 or smaller, drop the x. I guess when adding or subtracting it, right? Just like here. So what is smaller than 10 to the negative 4? 10 to the negative 5. 10 to the negative 6. Okay, let's see if you're following here. Gabby, here's a table. And let's say, well, you know you're going to have a quiz on this on Friday. I'm in a really bad mood when I write the quiz for Friday. Really bad mood. So that means I'm going to pick an acid that you have to do the quadratic formula on. Which one could I pick? Which one could I pick? And you have to do the quadratic formula. pick one specifically. Does anyone see what I'm driving at?
Strong acid.
Pick an acid. Which one would you say, oh, sure, I can't drop these X's on this one? Yeah, pick one. Pick one to show me that you're. Okay, phosphorus acid, I hear. Phosphorus acid, where is that? Okay. Phosphorus acid. Good. This is a good example of one that you do not want to see on a quiz or an exam. Because is this smaller than 10 to the negative 4? No. So this is when I'm in a bad mood. Right? You don't want to see that. But our K is 1.7 to 10 to the negative 4. Drop that X. We have this. Go ahead and solve for the X. See what you get. Take the negative log of it. You'll have your answer. All right? Make sure you can do this. So I got about 4.8, 4.77, something like that. And make sure you can get that. Okay? Oh, did I do it wrong? 1.7 to 10 to the negative 4 times 0.1 and then square root. Oh, that's supposed to be x squared. Sorry. All right, that's x squared. And then take the square root. Did I do this wrong? I did do it wrong. Oh, I forgot to take square root, didn't I? Square root, and then you do. So you do the square root, and you get your x to be 4.1 times 10 to the negative 3. See, that's what happens when you skip steps, right? Okay. Then I got to take the negative log of it. Just have it, it's already in the calculator. Just push log. 2.38. Ooh, that's a huge difference. Oh, yeah, but remember pH is negative log, so you drop the negative sign. Okay. Whoops. Does that make sense?
Yes.
So pretty much with all these weak acids, you have to write a Ka expression, do ice, and you can get any equilibrium concentration you want. Okay? So let's go to the boards, and we'll try to knock out as many of these as we can, get you comfortable and ready to do the homework,
So our X is
and we'll be good to go.
12 times 10 to the negative 3. The pH.
Okay. So let's try this first one up at the boards here and see how many of these we can get knocked out. Find the pH of 0.38 molar HCN. And the Ka is 4.9 times 10 to the negative 10. Running low on erasers. All right, so good. I like it. I see 2 people got 4.9 as the answer, right, for the pH. See if you can get that 4.9.
So this times this. It's there. And then. Oh, okay. This is good. Sorry. I just wrote it.
So somewhere around 4.8, 7, 4.9. Hopefully you're getting that, right? All right, make sure everyone's getting it. Make sure the folks around you are getting it. If you explain it to somebody, it's going to make it even stronger in your brain, right? Yeah, yeah. And we're going to drop that because it's 10 to the negative 10. Multiply, and then take the square root, and you have your x. Okay. So if you got it, try the next one. If not, let me help you out here. Yeah, you got it. Good. Now this next one has a little bit of a twist to it, but I think you can get it. It's the same idea.
You pH and you give H plus, and then you like put it into the concentration.
Yeah.
And then
I would do the complete ice table first, so you know how to plug in the Ka expressions. Be a lot easier. Yes, that is your x. You just got to figure out what it is, and you'll have it. Whoop, sorry. It can be anything.
Oh, okay.
It was our general way of writing any.
Minus one?
Yep, our general way of writing any weak acid conjugate base. Okay, do you have a game plan for number 3?
Kind of like working backwards.
Yeah, it is. It is kind of like working backwards. But I would make that whole ice table with x in it, because they told us what x is. If you do the whole ice table, they told us what x is.
Yes, they did.
Right? How?
When they gave us the pH?
When they gave you the pH, right? Because if you do the whole ice table, x is the concentration of H plus. And how do you get the concentration of H plus out of pH? 10 to the negative pH is hydrogen ion concentration. So I would do the whole ice table, complete that first, otherwise it's going to be confusing. Complete the whole ice table, figure out what your x is by using 10 to the negative pH, and then you'll have all the substitute back into your ice table, you have all the equilibrium concentrations, so you can calculate a Ka from that, products over reactants. But I personally would still write an ice table because it helps me from screwing up.
Okay.
So is this my H plus?
Yeah. Well, 10 to the negative 2.8, not 10 to the negative 28.
Oh, sorry. Well, let me do it. What if I want to do 2.8?
Yeah, well.
Molar, right, for E? Is it molar?
Yeah, concentrations are always big M.
That's right. You plug it in for X. And you have to write this way.
You look like an official coach.
Oh, okay. Yeah, you're right. I don't know why I wrote it there.
Just put it off a little bit.
All right. So did anybody get an answer for a Ka yet?
Yes, but I got the wrong thing.
Oh, I got the wrong thing. 4.84 times 10 to the negative 6. I don't know if anyone else has got it yet. Because H plus is X.
Oh.
Right? A minus is this one. That one is that one. So now you just write your Ka expression to substitute these guys in. Okay. A couple folks got 4.8 times 10 to the negative 6, at least 3, so I think that's got to be the right answer. Now, I guess you could drop the X, but you're taking a real chance, because what if your Ka's 10 to the negative 3 or something? So I wouldn't. Yeah, you're taking a chance. You're taking a chance if you drop it. But if you come out with a number that's really small, you're fine. You can drop it legit.
10 to the negative 6.
Yeah, so you can drop it legit. But if you got 10 to the negative 3 or 10 to the negative 2, you have to go back and not drop it.
Okay, so we just input it there. That's what you're saying.
And it's a calculator, so you might as well. I would just, why
Yeah,
drop it?
just-
And really get comfortable with your calculator. You can do all this in one step if you learn how to use parentheses. You can do 1.58 times 10 to the negative 3, hit x squared, hit parenthesis, 0.52 minus 1.58 times 10 to the negative 3, parenthesis, you got the answer. Right? Divide and use the parentheses. Yeah, about 4.8 times 10 to the negative 6. And no units on equilibrium constants. So make sure this works before you go on to the next one. Make sure you see why we did what we did.
I don't know what's wrong with calculating. Okay, 10 or 2.8.
Whoa, and that's not how we do powers. So if you want to raise anything to any power, you push this button. So you want to raise 10 to some power. So put in 10 first. Okay, you want to raise it to some power. So x to what power? Okay, 2.8 and make it negative. That's it. So make sure this works before you go on. Is it working for you?
No, I don't know what I did wrong. 0 for pretty, but I wrote
4 points for 10 negatives. Well, you're doing different rounding,
Oh,
right?
okay.
See, what I do, I put in First, I have 1.58 times 10 negative 3. But that's fine. Don't worry about it. So, but what you can do, though, Erica, is do all that in one big step on your calculator, right? You do 1.5 times 10 negative 3, square it, hit divide by, use the parenthesis, 0.52 minus 1.5 times negative 3, close parenthesis, equals, and you got it. I think most everyone's got this one. Go on to the next one. In number 4, we want to find the concentration of everything. Oh, is it, what units? Is it mole or big N? Yeah, that's
Is
the
big
question.
M? Is it big M?
It all depends on what this one is.
M.
Yeah.
Okay. I had M, but I
And it has to be big M. Because little m means something else. Molality. In comparison to molarity. Well, 0.15 molar solution of HF. So you put the 0.15s in the wrong spot. I could cheat off of somebody. Okay, get your x to be 0.01. Okay. So I think Crystal got, I think a lot of people got this. About 0.01 for your x on number 4. And then you just plug those back in for everything. You have the concentration of everything. Is that it? Or is there another one? We did them all?
I think so.
Woohoo! Oh, there's another one. If you want. I think it's the same thing over and over.
What happened was that when I would get to the log, I would press log twice. Like, I pressed it again, so I would get
Well, you
one
don't need
log.
log. There's no log in this.
No, I mean, like, I put 6.8, right? 4, and then times 0.15. And I press this, but I would press log.
Oh, there's no shift. You just want to square it.
Square root.
Oh, you want to take square root. So
Square
it's
root,
shift
yeah.
square root.
Yeah, but then after that, I press log on accident. I just
You
added.
get button happy. All right, if you want to work the last one, But it's kind of the same thing. Look, you guys are getting tired, so.